Welcome everyone. Today we're going to dive into a topic that often feels counterintuitive in the industrial world: preventive maintenance optimization. Specifically, we'll explore the phenomenon where too much maintenance actually creates more failures than it prevents. We are moving the conversation from simple calendar-driven activity to an economically justified strategy focused on loss prevention and value creation. The central question for leadership shouldn't be how many PMs did we complete, but rather, how do we know we are preventing the right failures instead of just consuming labor and eroding value? Optimization isn't about cutting corners or doing less. It's about precision, doing the right work at the right interval for the specific failure mode of your equipment. Our executive thesis is simple. While PM is essential, more is not automatically better. Every time we open up a machine, we introduce risks like human error, contamination, or infant mortality. Our ultimate goal is to achieve the lowest sustainable business risk at the lowest total lifecycle cost through data discipline and failure mode logic. To guide our discussion, we've structured today's agenda into 6 parts. We'll start with why this matters to the board, move into the technical reliability logic, translate that into financial impact, design an optimized strategy, and finally, look at governance and real-world case vignettes. Let's begin with part 1, why this topic matters. We need to understand why PM optimization is a critical board-level issue rather than just a task for the maintenance shop. Management must care because maintenance strategy directly impacts EBITDA, cash flow, and safety. Over-maintenance is a hidden drain that hides in labor budgets and spare parts consumption. If we reward busyness instead of value, we end up with a plant that looks active but remains fundamentally fragile. There is a hidden paradox in our industry. When things fail, our instinct is to add more tasks and checklists. This leads to PM congestion, a state where constant interventions actually steal capacity from precision work and defect elimination, making the maintenance system an engine of failure rather than a shield against it. To be clear, PM optimization is a disciplined review of tasks and intervals to find the best mix of predictive and preventive work. It is not a blunt cost-cutting exercise or a mandate to stop all time-based work. It is a technical process, not just a dashboard project. So, what does over-maintenance look like in practice? It shows up as frequent, intrusive inspections without clear logic, rebuilds triggered by habit, and a culture where everything is critical, leading to PMs constantly being overdue. Most tellingly, it's when failures occur shortly after a maintenance event. If you are an executive, look for these symptoms: high PM compliance alongside high emergency work, a routine backlog that moves slowly, and skilled labor tied up in repetitive tasks while the same bad actors keep breaking down. It's the sound of a lot of activity with very little stability. Now that we've set the stage, let's move to part 2, the reliability logic. We need to understand the why behind the failure creation mechanism of excessive PM. A common misconception is that all equipment wears out linearly with age. In reality, a huge portion of industrial failures are random or process-induced. If a failure isn't age-related, simply increasing the frequency of a calendar-based PM won't reduce risk. It might actually increase it by disturbing the system. We often talk about the bathtub curve, but it's frequently misused. Stable operations benefit more from condition monitoring than arbitrary teardowns. We should only justify age-based action when age is demonstrably the primary cause of failure. Otherwise, we are just resetting the clock to the infant mortality zone. How exactly does excessive PM create failure? Intrusive work disturbs stable systems. Every time we open a gearbox or realign a pump, we risk misalignment, fastener errors, and contamination. Furthermore, the constant start-stop cycles required for PMs create thermal and mechanical stress that wouldn't exist in continuous operation. We can categorize these maintenance-induced failures into physical and system mechanisms. Physically, we see things like improper torque or lubricant contamination. Systemically, we see rushed execution to meet targets, poor parts quality, or a lack of post-maintenance verification. Both are results of an overloaded PM schedule. To manage this, we must distinguish between intrusive and non-intrusive tasks. Teardowns and overhauls are high risk because they reset stable conditions. Conversely, non-intrusive tasks like vibration analysis or infrared thermography allow us to monitor health without introducing the human tax of manual intervention. Often, our calendars defeat physics. OEM manuals provide conservative baselines, but they don't know your specific operating environment. A time-based task is only justified if the probability of failure meaningfully changes with age and if the task itself is technically effective at mitigating its specific failure. Forced overhauls can backfire because new parts don't guarantee reliability. Precision installation does. Many chronic problems are better solved by design corrections than by repeated overhauls. We should let condition and economics drive overhauls, not tradition or a date on the calendar. Consider this post-overhaul trap. A machine is running stably. We overhaul it just because the calendar says so. During the rebuild, a small error occurs, perhaps a clearance shift. Upon restart, the asset fails early. The organization blames old age, but the intervention itself was the accelerator. Moving from the engineering floor to the finance office, Part 3 explores the cost, capacity, and value leakage associated with these maintenance choices. The cost of excessive PM is much higher than just craft labor. It includes the planning, the scaffolding, spare parts burn, and most importantly, the lost production capacity and startup yield losses. We must account for the failure probability we create ourselves. This graph illustrates the optimization curve. At low maintenance intensity, downtime costs eat your profits. But at high intensity, PM labor and intervention risk become the dominant costs. Optimization is the sweet spot that minimizes the total lifecycle cost, not just the downtime. Over-maintenance is essentially a capacity thief. It takes up planned downtime windows, requires line interruptions for access, and forces high overtime to catch up. This leaves no room for engineers to focus on the root causes of recurring bad actor problems. From a board perspective, we must ask, which tasks are actually protecting critical assets? What happens if we extend an interval? And where are we seeing repeat failures after work? We need to release the trapped capacity currently tied up in low-value routine work. Now let's look at the how. Part 4 covers designing an optimized PM strategy that focuses on value over activity. Our first design principle is to preserve function, not tradition. We should analyze functional failure modes rather than just following inherited checklists. Every PM task must earn its right to exist by showing it effectively reduces a specific risk. We start with asset criticality. Not every pump or motor deserves the same level of attention. Criticality defines the rigor. High-consequence assets deserve deep optimization and strict quality control, while others may require much less frequency or precision. Task selection must be based on the failure mode. If it's age-related wear, use scheduled replacement. If it's random, use condition monitoring. If the failure is low consequence, run to failure might actually be the smartest strategy. And for chronic design flaws, don't just maintain it, redesign it. This decision logic represents a disciplined path. Identify the function, define the failure mode, assess the consequence, and only then select the task and interval. Any task that cannot be technically or economically defended is a candidate for removal. It's important to note that run to failure is a legitimate strategy for low consequence, inexpensive items. It is not neglect. It is a deliberate choice backed by preparedness and spare parts availability to avoid the maintenance tax on non-critical assets. Condition-based maintenance, or CBM, is our preferred alternative where detectable PF intervals exist. This means moving from doing maintenance because it's Tuesday to doing maintenance because the data shows a threshold has been crossed. Optimization often means converting intrusive PMs into these smarter, non-intrusive tasks. When optimizing intervals, we don't just delete work blindly. We review history and operating data. We lengthen intervals where stability is high and shorten or redesign them where degradation is escaping our current checks. We pilot these changes first to verify the outcomes. Precision maintenance is actually a PM optimizer. By improving alignment, balancing, and lubrication standards, we eliminate the need for many repetitive routines. One high-quality intervention often does more for reliability than 5 mediocre ones. Work management discipline is the glue that holds this together. Even an optimized PM will fail if planning, kitting, and procedures are weak. We need stable schedules and clear acceptance criteria to ensure that the work we DO perform is done correctly. In Part 5, we look at governance and metrics. How does leadership ensure that these optimization efforts are sustained over time? Optimization requires data. We need a clear asset hierarchy, meaningful failure coding, and a record of both labor and parts costs. Most importantly, we need to track condition findings and the status of post-maintenance defects. Watch these leading indicators. A healthy program sees condition findings closed on time and repeat failures trending down. A warning sign is high PM compliance paired with high emergency work. That's a clear signal that your current PM tasks aren't actually preventing the failures occurring in the field. We recommend a balanced dashboard. Avoid managing by a single number. Executives should look at reliability, work quality, and economics together. Remember, PM compliance is just one metric. It is not the strategy itself. We must debunk the PM age compliance myth. A plant can have 98% compliance and still have terrible reliability if the tasks are wrong. Boards should demand evidence of loss removal and capacity protection, not just a high percentage of completed work orders. An executive dashboard should highlight your most valuable assets, your largest recurrent losses, and repeat failures within 90 days of maintenance. It should show the craft capacity being released from routine work to be reinvested in improvement projects. So, how we get started? Part 6 provides a roadmap for implementation and leadership action. In the first 90 days, you should baseline your current portfolio and identify your bad actors. Select one pilot system. Review its PMs for technical basis, deciding whether to keep, change, or remove them, and build post-work verification into your work packages. Over a 12-month roadmap, the goal is to build the operating system before scaling. Each phase should provide evidence of labor released and risk reduced, ensuring that the change is grounded in measurable results. Everyone has a role. Operations provides context, maintenance ensures quality, and engineering handles the logic. Leadership's job is to prevent this from becoming a cost-cutting slogan and to ensure that compliance targets don't overshadow task quality. When choosing your first pilot, pick a system with clear business consequences and good data, but avoid overly political areas until you have a win. The goal is to create a visible success story of improved reliability and reduced low-value work. Change management is vital. Technicians might fear understaffing, and operations might fear breakdowns. Leaders must communicate that this is about better risk control, not less care. Celebrate removed tasks only when asset performance remains stable or improves. To wrap up, Part 7 uses real-world case vignettes to test the logic we've discussed today. Vignette 1 focuses on overservice pumps. One plant rebuilt pumps every year out of habit, but the failures were actually due to seal contamination and misalignment. By moving to CBM and precision standards, they improved reliability while doing less intrusive work. The wrong task leaves the true failure mechanism untouched. Vignette 2 shows the danger of calendar motor overhauls. Annual shutdowns were reintroducing infant mortality due to inconsistent installation quality. By moving to condition assessment and evidence-based triggers, the site avoided disturbing healthy equipment and improved uptime. Vignette 3 highlights lubrication route overload. A technician was touching hundreds of points regardless of need, introducing contamination risk. Redesigning the route based on criticality released labor for oil analysis and high-value work. Not every repetitive task protects value equally. Here are 5 questions for your next board discussion. Which tasks are just historical carryovers? Where is our labor being wasted on low-risk work? And most importantly, what financial evidence do we have that our PM strategy is actually creating value? To conclude, here's what to stop and what to start. Stop treating volume as a virtue, and stop opening healthy equipment without a reason. Start governing PM as a risk control system. Use condition data to replace intrusive work, and measure the capacity you release. Our key takeaways. Too much PM can create failure. Optimization is achieved through logic, effectiveness, and governance. The question is not how much PM, but how much risk are we removing per hour? Demand value-based strategy, not just activity-based reassurance. Thank you for your time. This presentation was prepared for professional discussion, and I encourage you to validate these concepts against your specific site data and safety standards. I am now open for any questions or further discussion.